Hello everyone, my name is Marios and I work as a developer relations engineer at HTC VIVE. It's a pleasure to be here with you today in a virtual environment, and I would like to thank the organizing committee of Laval Virtual 2020 for the invitation. During this presentation, I will try to give you an idea of what you can build as a developer utilizing the VIVE software development kits and exploring the potential of VIVE products. So first, let me highlight that as HTC VIVE, we recently rode the wave of virtual events, and the annual VIVE Ecosystem Conference this year was actually held in VR. Despite the difficult situation with COVID-19, it's nice to see events like Laval Virtual going online and not getting cancelled, as this gives us the chance to share new things with the developer community and stay in touch with you. Our plan is to continue to do so in the future, so we have a series of online events coming up, and we'll talk about this later. Now, HTC VIVE has an exciting new VR product lineup for 2020. Apart from VIVE Pro Eye, that offers integrated eye tracking capabilities, we recently revealed a handful of new headsets and faceplate joining the Cosmos family, each of which was designed to serve the needs of both consumers, businesses, and of course developers. Now, the best feature of VIVE Cosmos is its modularity. Although by default VIVE Cosmos is an inside-out tracking headset, you can swap the faceplate to use the external base stations and convert it to an outside-in tracking solution, or you can use the other faceplates to blend, like the XR faceplate, to blend the real and the virtual world. Now, this talk is aimed at developers that want to make the most out of the new capabilities of these devices, and of course the SDKs that support them. Over the last 5 years, we have accumulated several different SDKs. This table actually that you can see lives on our website, and it's quite useful if you need to determine the SDK compatibility that supports your VIVE device. As you can see on the left-hand side, we have the original VIVE and then the VIVE Pro family. We have the Cosmos family, and of course the Focus series, which is our standalone headset family. Now, the VIVE Sense SDK that you can see on the top, it's a framework to develop VR applications, allowing you to redefine how you interpret and interact with the new realities. This category includes SDKs that map to our senses. So we have the eye and hand tracking SDKs, and then we also have the SRWorks SDK that allows you to fuse the physical and digital surroundings. We also have an interesting Unity plugin called VIVE Input Utility, targeting many different platforms from a common code base that's allowing you to quickly build VR applications and deploy to different headsets, and provides functionality for you so that you can focus on the content and not spend too much time developing the application. Now, VIVE Wave is an API in Runtime, which enables the developers to create VR content on Android, and provides a flexible and simple interface for VR. Again, using it, developers can actually focus on designing awesome and immersive VR experiences without requiring the specific knowledge of each different VR hardware. So we also provide a number of APIs for additional OEMs to use this platform. Finally, we have VivePort. For those of you who don't know, VivePort is our VR app store, compatible with a range of different devices from HTC. We also support other Steam VR devices, as well as devices from partner companies. And although the VivePort SDK is not required if you wish to distribute your title on the VivePort store, it still provides many useful features for your content, such as leaderboards, DLCs, in-app purchases. So it may be also useful for you to have a look at it on our website. Today, we will focus on the VIVE Sense category, and I'll focus more on it in this presentation. So as I said, if you want to learn more things about all those SDKs and find that table, you will find everything you need online at developer.vive.com. Feel free to visit the website after this presentation and explore it. Also, most of our SDKs are just a click away, grouped together for your convenience, as we try to make this process easier for the developer community. Developer.vive.com/resources, and here you can see you can find every SDK in different groups, and all the files and everything you need, especially if you've done this before. You can easily come to this website to quickly download what you need. Now, it's worth noting that we also have a developer forum where you can find interesting tips, you can ask questions, or share information about your projects. And this is a useful resource if you want to be up to date with the latest releases of the SDKs and, of course, get support for them. We're really eager to listen from you and get also feature requests or any other information that you feel like you need to share. So let's start with the VIVE hand tracking SDK. This SDK is actually a cross-platform tool that utilizes the front cameras of the VIVE headset based on a deep learning model, like most hand tracking solutions do. So with it, we can track both hands at the same time and detect whether they are left or right. It can currently also recognize up to 6 predefined gestures, and these include the OK gesture, pointing, thumbs up, 5, fist, and victory. But of course, we're also looking into adding more of these in the future. Now, our hand tracking engine can provide the following modes. We have the 2D point mode that allows you to get a 2D point, so X and Y coordinates, for each detected hand. In this case, this point is always in the plane that is 25 centimeters in front of the camera. We have the 3D point mode that is supported on all dual camera platforms, so all dual camera headsets, and you can get a 3D point for each detected hand. And finally, on powerful devices, we can have a skeleton mode with 21 3D key points to form a complete skeleton. Now, this skeleton mode, which is essentially finger level 3D positional tracking, consists of tracking 21 points on each hand. So it's 4 per finger, as you can see, and 1 on the palm. The information from all those 21 skeleton joints can actually be mapped to a custom 3D hand model, and we actually provide some example models for you, and then you can actually use them to bring your hand from the real world into the virtual one. Now, in this video, you will see the abilities of the hand tracking SDK. This one runs on VIVE Pro in skeleton mode. The complete skeleton of the hand is actually rendered with key points and links, and the color of the link indicates the gesture type detected. When there are multiple hands, the color of the key point is used to distinguish between the left hand and the right hand. And when you move your hand and fingers, the skeleton, as you can see, will update accordingly. Now, what's really great, and many people don't know about it, is that the hand tracking SDK supports most of our headsets and even our original VIVE, as well as some Android phones. This table shows you which modes are supported for each platform, and as you can see, since the original generation of VIVE only had one camera, it doesn't support 3D positioning, but that single camera can actually give us a 2D point for the hands. So if you still want to experiment with VIVE hand tracking SDK, and you only own the original VIVE, you can still do that. Now, here's what happens when you download the SDK. The first thing you're going to see is on the right-hand side here, you can see when you download the SDK from our website, you'll get a zipped up package containing support with a few different files. One of them has support for Android. You have pre-built demo samples, so an exe file that you can quickly run to test the hand tracking solution. You have a folder called Unreal and C++ that contains the Unreal plugin and native C and C++ files, as well as the full online documentation and the latest Unity package. In the latest release notes, you will notice that version 0.9.1 is the latest release. It was released last month, and you will notice that we are continually improving the tracking experience. And finally, the documentation is also available online to make it easier for developers to understand what the SDK can do before even downloading it. Now, this sample demo that you can see here on the screen illustrates several things, including interactions directly with objects and remote interactions, such as remote grabbing with the use of single and multi-hand gestures. The sample project shown here is actually included with the SDK with full source code. So if you want to see how this is done, you can just have a look at the source code of this demo. Now, all platforms are supported equally. So, but in our case, the core for both the Unity and Unreal APIs is actually the C and C++ API, as actually libraries are provided to talk with the hardware. And we also have Java for Android, of course. So what we're going to do now is take a look at the core APIs that are used, and these are the ones that Unity and Unreal are using as well. So let's have a look at the basic functions for starting and stopping the gesture detection. We look at as you said, we look at the C API first because that's the building block for the plugins used in Unreal and Unity. So you will need to specify two things. First of all, you need to specify the backend mode. So whether the system should use the CPU or the GPU, or whether it should automatically figure out which one is the best to use. And then the gesture mode that we mentioned earlier, so the 2D point, the 3D point, or the skeleton mode. Now, if a mode is not supported on device, then the system will automatically fall back to the previous supported mode. And it's worth mentioning that although start detection is a non-blocking call, stop detection will actually is actually a blocking call until the pipeline is stopped. Now, both Unity and Unreal plugin are based on a native plugin, as we said, and provide some advanced features for ease of use. In Unity plugin, a gesture provider script should be added to the render camera. This script is actually handling the starting, stopping, and pulling results automatically based on Unity's monobehavior lifecycle. Now, hand detection, it's worth mentioning the hand detection only runs when the script is active. On the other hand, in Unreal, what you need to do is add the VIVE hand tracking component to an actor in your scene. And then you can just use the blueprint functions mentioned here to start and stop the gesture detection. And here's how to obtain the gesture data. Now, using the function getGestureResult, you can get a struct and enum that represents all you need to know about the gesture being recognized, and of course the position points. You get 3D points for each joint if you use the skeleton mode, and the data can be updated every frame. As you can see, all the gestures that I mentioned are here in that enum, and all the points are actually in an array. And here's how to actually get the left and right hand results directly. Call from your main loop. For example, in Unity you can do that in the update function, or in Unreal Engine you can do this with Eventic. You can also check to see if there's been an update in the current frame to avoid any additional processing if there hasn't been an update this frame. And we also, in Unreal Engine, we also support blueprints, so you can see how easy it is to query the left hand or the right hand and then get that array with the 21 joints, the current gesture type, and whether or not it's a valid one. And here's a view of the sample project again. Initially, you can see how we use a gesture to toggle between skeleton hands and robot hands. But this video is actually showing how interactions using the model's colliders to pick up a cube. As you can notice, using just the colliders, it's tricky to grab the cube. But you can combine the gesture recognition, and specifically the OK gesture, to initiate the grabbing mechanism. So let me play just the video again. You'll notice that when you're trying with your right hand side, you'll notice the difference. The right hand is only using colliders, while the left one is using both colliders and gesture together. I'll play this one more time. So you see here with your right hand, it's a bit tricky just with the colliders, but the left hand is actually takes the OK gesture and then grabs the cube. Now, to illustrate this further, I can show you how difficult it is to pick up a tiny cube with colliders alone. That's why you should always think through the options you have for grabbing with hand tracking. You need to try and combine existing solutions or come up with new ones to make it seamless. So you don't just want realistic interactions and relying on colliders alone. You need to also make use of the gestures as well, or use, of course, third-party software that already has a better solution and that you can exploit in this case. Now, earlier we saw how we can grab things remotely. Here's how you can use a gesture, in this case the natural point gesture, to turn on the laser pointer and remotely select menu items in a standard Unity UI. That's something that you would normally do with VR controllers as well, just using raycasting. And you can simply repurpose your raycaster to emit from the tip of your index finger instead of your controller. In fact, you should be able to reuse most of the same code as if you were just using controllers, which makes the integration even easier. Notice how natural it is to use a poke gesture to indicate the button click, much like the collider way of pressing a button that we have already seen in most applications. Now, here's an interesting use case from Acute Art that integrated hand tracking for one of the projects. Acute Art is actually working together with renowned international artists to produce compelling immersive experiences where the viewer becomes participant and player. In this case, you can see how the developers used our hand tracking SDK and simple gesture recognition to add interactions with the objects. And it gives you an idea of how interesting it is to use the hand tracking SDK and how it makes the experience more immersive as well. So I'll leave this running to enjoy this application. The developers managed to really easily integrate hand tracking in just a few days. And you can see that it enables, you can see here, just using a gesture, you can actually turn on the TV, for example. And it gives you an idea of what you can do, just add simple interactions, hand interactions in your application. Now, the hand tracking SDK is actually updated quite regularly, and this list contains the roadmap for future releases. So you should expect support for the pinch gesture, as it is a gesture that is often used in interactive applications. But we will also provide a way to be able to identify custom gestures as well, depending on your needs. So you no longer need to rely on the predefined gestures. Now, the next update is also going to include the new hand model that will help with your tests and experimentation. And we also plan to support other devices, such as Valve Index. And since we already work under OpenVR, this is something that can be done by adjusting according to different camera characteristics and applying some deep relearning to our model to match the new specs. So please give it a try, download it today, and here are the direct links, but you should also be able to easily navigate and find it from developer.vive.com. Please also check our forum, as we have our engineers there available to answer all of your questions. I also hang out on that forum as well. And in addition to the above resources, I'll be posting additional code that you've seen here on GitHub. So just search for VIVE or VIVE software. Okay, so let's move on now to another topic, which is eye tracking. So what is eye tracking and why actually is it important for VR? Eye tracking is a technology that enables a device to measure eye position and eye movement. It can actually determine where your attention is and what you're focusing on, as well as facilitate natural and intuitive interactions. Eye tracking also allows capturing real-time analytics and insights, which can lead to better business intelligence for enterprises. For example, the German car giant BMW, together with Zero Light, leveraged precision eye tracking to do two things: reduce the rendering workloads and overhead, and also capture better business intelligence through analytics. To put it simply, eye tracking is the most impactful innovation in VR, and that's exactly why, as HTC Vive, we created and launched Vive Pro Eye in 2019. It was actually announced at CES 2019, and it features integrated built-in eye tracking. Now, HTC provides an SDK for eye tracking called SR Anipal SDK. It stands for Animation PAL. In this list, you can see the features of the API provided. So developers can actually get the position and diameter of the user's pupil, as well as the eye openness as a normalized value. You can also quickly query and get the object that the user is currently looking at, and you can of course get information regarding the gaze vector, so the ray that is emitted from the user's eyes depending on where he's looking at. Beyond that, you can use the SDK to drive the facial animation of avatars using eye blend shape animations for the avatar. And the most important feature, I would say, is the fact that you can combine the SDK and the VRS plugin to exploit foveated rendering. So we'll talk more about this in detail soon. So to summarize, here are some ideas for eye tracking use cases. First of all, as I said, foveated rendering will be a must-have in the future for those applications that actually want to raise the bar of visual quality and keep performance high. Analytics is another obvious use case, which is really important for improving games, apps, and commerce. And then aim assist, actually, for shooting and throwing is a really great mechanic for games and training. It really feels great to shoot an arrow where you're looking at or toss something where you're looking at. Then, of course, expressive avatars. Today here, every one of us is actually using an avatar for Laval Virtual. So imagine being able to actually have the avatars move their eyes according to our actual eye movement. So it's a great social VR feature. And similarly, you can actually use eye tracking and record the eye animations, and then use them for gaze-aware NPCs for games and, of course, training. So it makes it easier to actually generate those animations instead of having someone create the animations manually. So if you want to try the SDK, you can visit our website and you will need to download two different files. The first file is an installer for the required runtime that runs in parallel with the application. And the second file is a zipped folder that contains all the plugins for Unity and Unreal development, as well as the sample code and the demos. Now, when you install the runtime and run it, you will notice a small robot icon on the Windows tray. This icon's eyes will turn orange if a headset with eye tracking capabilities is detected, but the device is still in idle mode, and it will turn green if a program is retrieving eye data from it. So make sure the runtime is always running while using the app. And of course, this tray icon can show you the runtime version that you're currently using. Now, before you can use eye tracking, it's really important to calibrate the software. This is required for each new user, and the calibration results are saved to your PC. So as you can see here, to start the eye calibration, what you need to do is select the VIVE Pro Eye button at the bottom grid of Steam VR menu, and then hit Calibrate. Then you will be asked to adjust your headset to fit to a specific virtual frame. And then you will be asked to adjust the IPD value by rotating the IPD knob until it matches again the virtual box. Once this is done, you will be guided to do gaze calibration. So you need to look at the blue dot sequentially, so not the center, right, bottom left, upper left, and lower right of the panel until the calibration has been successful. You need to be careful to only move your eyes and not your head. And then after that, you'll see this mini demo application. You can try a mini demo to light up the dots with your eye gaze, or press the VIVE controller system button to quit eye calibration. That's it. You're actually ready to develop eyewear applications. So now let's see how easy it is for the developers to use the API of the eye tracking SDK and get information about eye tracking. As you can see in the code example on the right here, we provide an API to update and get the eye data struct every time. And this struct contains information about the pupil diameter and position, as well as the eye openness, while also you can quickly and easily get the gaze direction. This eye data struct contains information for each eye, and there is one for combined view. So on the left-hand side here, you'll see the structure of all those different data structs. And as you can notice from the API here, it's really easy to access the data. You just need to call this every frame and then query wherever you need for your application. So quite similarly, we provide functions to get the object the user is looking at and the blend shapes for the animations of the avatars. Again, that's a really easy to use API for both Unreal and Unity, and it makes it really easy to integrate eye tracking in your application. You don't really have to go through many code changes to make this work. And I'm sure that you always love demos, as I do. So here's a demo that shows you how you can apply the data for the pupil position on the left and the eye openness on the right on a human avatar. The SDK actually comes with a sample demo, so you can quickly understand how to use the code base. And you'll notice how natural this human avatar looks and how this greatly improves the sense of immersion in the virtual world. You instantly get the idea that this is actually a real human. And that's because it is, because it's the eyes of a real human are being tracked here. Okay, so here's another demo showing you how you can create a gaze ray based on the information from SDK and how you can quickly get the focused object. As you can see, the gaze rendered is raycasted from the middle of the user's eyes, and when it collides with an object in the scene, we get a text. The text is getting updated with the object name. So you see green cylinder here, red sphere, red cube, blue cylinder. So again, it's really easy, and it shows you what you can do with the SDK. Now, HTC VIVE also created the lip tracking module. You probably noticed on my slides that this is an eye and lip tracking SDK. The lip tracking module it can actually be used with the SR-Annapel SDK. We're actually working with developers and enterprise customers that are interested in experimenting with it for potential applications. This is a simple camera that can be attached to the VIVE Pro eye headset and allows developers to build VR applications that reach new levels of immersion, since you can now the avatars can actually mimic both the eye and the mouth movement of the users. It's worth noting, though, that the HTC VIVE lip tracking module is not a consumer device and is not planned for sale currently. Here in this example, you can see how a company called Neos VR, this is an application for social VR, used it to change the way the avatars look in the environment. And as I said, you can actually track the jaw, mouth, and cheeks and tongue as well. And here's another example which is included in the SDK and supports the lip tracking module. It's called Face Gym. The user can actually change between different avatars, humanoid or not, and the lower bottom of the avatar will move according to the user's facial expressions. Now, using the SDK with different avatars shows you a glimpse of what we're able to do in social VR applications. And with all the online and VR events coming up, this sounds like a great addition for the future. So notice how nice it feels to also change the avatar to a non-humanoid avatar. And imagine how this can be used for games as well. Okay, so let's go back to eye tracking for a second and focus on foveated rendering. As I mentioned earlier, foveated rendering is the main reason why eye tracking is the most impactful innovation in VR. Now, often creative directors and technical artists try to raise the bar of visual fidelity in immersive VR applications, but the engineering teams often hit this bottleneck of achieving the required minimum FPS, especially when new headsets are released with better and better display resolutions. And that's exactly where foveated rendering comes into play and allows us to quickly and easily improve the graphics performance of VR applications with minimum effort. HTC VIVE worked with NVIDIA and integrated the variable rate shading technology in a plugin that can be used in both Unity and Unreal to easily enable foveated rendering. Now, for those of you that don't know what foveated rendering is, the term foveated derives from the word fovea. Fovea is the part of the eye retina that allows us to have a sharp central vision, which is called foveal vision, and lets us focus on the visual details of what is important in a narrow region right in front of us. The foveal and parafoveal areas cover a field of view of about 5 degrees. Now, anything outside the fovea region belongs to the peripheral vision, and despite the fact that peripheral vision is also useful, it can only detect moving content, changes, and color. And that's why we feel it a bit blurry and less detailed. Now, foveated rendering technique exploits the anatomy of the human eye that we just described and suggests that computer can drop the quality of graphics in the peripheral vision by lowering the resolution there, while focusing all of the available processing power on the smaller foveated area of the image that matters. And it's worth noting that there are two types of foveated rendering, and people often confuse the two. Fixed foveated techniques have been used to roughly adjust shading rate based on lens characteristics of headsets. It assumes a forward viewing direction always and limits the rendering cost of display areas, which are not clearly visible in the headset, mainly around the lens distortion region. Now, dynamic foveated rendering requires eye tracking to accurately render based on gaze direction. So these two things are quite different. Now, although the concept of foveated rendering has been around for a while, the NVIDIA Turing architecture for GPUs is what allowed the use of rendering technique called VRS, or variable rate shading, that can enable this feature. VRS offers the ability to vary the shading rate within a frame. So instead of executing the pixel shader once per frame, with VRS the GPU can not only apply a single pixel shader operation to a whole 16 by 16 pixel region, but also we can dynamically change the shading rate during actual pixel shading in one of two ways. So it allows us to use core shading, and in that case what happens is that we can execute the pixel shader once per multiple raster pixels. For example, we can do this once in a 2 by 2 pixel area, and then we can copy the same shade to all those 4 pixels. And the other thing we can do is use supersampling. So with supersampling, the pixel shader is executed more than once per single raster pixel for better results, especially when it has to do with text, for example. Now, this fine level of control enables developers to combine varied shading rates and gaze tracking capabilities for foveated rendering. And here are the requirements. As I said, you need to make sure that you have a graphics card that supports foveated rendering. And of course, you'll need a VIVE Pro eye headset, as we'll show soon. We'll need to actually feed the eye tracking data into the foveated rendering plugin. So in the following slides, what I'm going to do is show you how to enable foveated rendering both in Unreal Engine and Unity. Now, currently, if you want to integrate VRS and foveated rendering in your Unreal Engine project, you need to download and use a custom modified version of the Unreal Engine source code and build it yourself. This is available on the HTC VIVE GitHub repository, and we also have a link on our website now. That's mainly because we had to modify a few things in the rendering pipeline source code of Unreal Engine to support the VRS render passes. However, we're working closely with NVIDIA and Epic Games to make this process easier in the future by integrating the required engine changes to the official Unreal Engine branch, so that in the future the VRS plugin will be the only thing required and you don't have to use a custom engine build. Nevertheless, it's worth mentioning that the changes we made in the engine are only a few lines of code, so you can easily do the same thing if you're working with a custom version of the engine already. Now, after you download and build the engine, you will notice that the VRS plugin is already installed, as it comes together with the engine. And you will also need to install the SRNPL SDK plugin after you download the SDK from our website, as I showed before. This is important because these two plugins will need to communicate together. We'll show more details in the next slides. Now, what we need to do is tie those two plugins together. So we will combine the SRNPL plugin and the VRS plugin to enable foveated rendering by feeding the eye gaze data each frame to the VRS algorithm. The only thing you need to do is create a new function to return the normalized eye directions using the SRNPL method we showed earlier, that is called getVerboseData, and expose it to blueprints if you want to use it in blueprints as well. After that, the only thing you need to do is feed the normalized eye directions to VRS plugin, and especially use the method called update stereo gaze data to foveated rendering. And this way, the center of the foveated region for every frame will be calculated by the VRS plugin automatically. That's mainly it. The only other thing you need to make sure you have enabled is you need to enable eye tracking in your scene. In Unreal Engine, that's really easy. You just need to drag and drop the SRNPL eye framework actor in your level and just tick the enable eye tick box. And that's it. That's all you need to do. And apart from that, if you want to change a few things in foveated rendering, make sure that in the project settings you have enabled foveated rendering. So what you also need to do is to enable eye tracking in your scene, and that's really easy. You just need to add the SRNPL eye framework actor in your level, and then you just need to tick the enable eye tick box that you'll find in its properties. Now, the last thing you need to do is just go to the project settings, find under the VRS settings category, and tick the boxes to enable VRS and eye tracking. And that's it. You can even tick and untick the settings while being in VR preview mode without having to restart your application. The other thing I want to mention is that the VRS plugin allows you to configure the shading rate of each region according to your needs, and of course according to the type of your application. In the project settings, you can choose from highest performance all the way to highest quality, depending on what you need. This property adjusts the shading rate of each region automatically according to a predefined rate without having to specify any numerical parameters. However, if you wish to do so, you can select the custom option and select the shading rate yourself to experiment and find the best result that suits your app. Similarly, you can adjust the radius of each foveation region for the innermost, the middle, and the peripheral area. You can switch between narrow, balanced, and wide, and these options contain predefined values for the horizontal and vertical radius of each area. Or again, you can just pick the custom option and select your size yourself to suit your needs. Now, in Unity, things are a bit easier since we don't need the custom engine. You only need the plugins. What you need to do is download the plugin from GitHub or from the Unity Asset Store. And after that, in your project, just make sure that VR is enabled in the Unity project settings. And you'll need to define a new symbol, which is use_SR_enable. Make sure that from the package manager, OpenVR is installed as well. Now, what you need to do is, again, import both the SR-enable eye tracking SDK. We have a Unity plugin for that. And of course, the VRS Foveated rendering Unity plugin. It's the same reason why as before. It's because we need to feed the eye tracking data to the VRS plugin. Now, after that, what you need to do is attach the SR-enable eye framework script to your main camera and tick the box Enable Eye. And then, of course, for foveated rendering, do the same thing. Use the VIVE foveated rendering script and attach it to the main camera. And here again, you can easily mess with the settings. You can actually customize them. It's exactly the same panel as the one in Unreal. Now, we actually tested the performance improvement with foveated rendering using some of the scenes included in Unreal Engine sample scenes pack. Now, in this case, you can see the virtual studio scene that showcases Unreal Engine's ability to integrate with professional quality video cards and contains high quality screen space reflection, which is benefited by VRS a lot actually. So the frame time here was improved by about 45% when using the narrow and highest performance presets. Now you probably see those two, you don't notice a difference between the two images, but then one on the left is without any foveated rendering, and the one on the right is with foveated rendering and narrow and highest performance presets. You may notice a slight pixelation, but that's because that's from the area outside the fovea. Now, if you pick the balanced and balanced presets, we still get an amazing performance increase of 30%. And you'll see that the difference, you can't even notice the difference at all. And that's the great thing with foveated rendering. The user won't really understand that anything changed, but actually the performance increase is great. So again, here are some quick tips. Take into account that based on our tests, using the balanced option for both the foveation pattern and the shading rate will give you the best result for quality and performance. Now, foveated rendering through VRS is not really useful when it comes to scenes that have many dynamic objects, unfortunately. So if you have a scene with many skeletal meshes, avatars, and particle effects, you won't see a great performance increase. However, for static scenes with reflections and details, the performance gain is great. As you saw previously, and based on an average from our tests, we saw a performance increase of about 20 to 38% just with a few small changes in your app. And that's exactly why foveated rendering is a big thing. And we consider it a must-have for VR applications, especially for the applications that want to achieve a better visual quality but maintain the high FPS and good performance. Okay, so the last SDK we'll talk about today is actually the SRWorks SDK. And before we start, let's revisit what extended reality is all about. Now, XR is actually a big umbrella covering the entire continuum all the way from reality to virtual reality. So for the future of XR development, an application should be able to jump between these two quite easily, and our SDK can actually help you do just that. Now, utilizing the dual camera VIVE headsets, we can acquire a digitized stereo view of the real world, mimicking human vision and mixing it with virtual objects. VIVE Pro was the first headset that supported the SRWorks SDK, and this SDK actually expands the capabilities of this technology and provides a series of modules to help developers connect the real and the virtual world. This way, the same device is able to combine both augmented and virtual reality 2 in 1. So here's an example. It may be tricky to understand this. This is a sample demo. What you see is a user wearing a VIVE Pro and looking at the physical room. He throws virtual objects in the physical room, and as you can see, there is realistic physical collision between virtual and real objects. And the user can also spawn a portal to connect real and virtual worlds together and interact with them. As you can see, the player can even step into the virtual world inside an immersive VR environment. He can still interact with the real room as well, so you can see how he's throwing objects, and collision is handled properly in its case. And of course, the user can either just shut down the real world room and go back to VR only, or you can open a portal back to the real world again and go back to the real world again. So it's amazing how fusing these two worlds together can give us new ideas for the VR apps. Here's another idea just for games. For example, you can play golf just with those portals. But yeah, it gives you an idea of what you can do with this SDK. Now, I need to highlight something. There's a difference between the optical and video see-through systems, as many people often confuse these two. Now, optical and video see-through systems differ on how the real world is captured by the device. VIVE Pro, for example, uses a dual camera to simulate stereo vision. This approach is actually called video-based, shown on the left-hand side. And that's because it acquires a digitized image from the real world, from the dual camera. It then mixes it with computer graphics generate images, and then it shows the mixed result on the display in front of its eye. Now, this approach is easier if you want to achieve true occlusion, because you're able to manipulate each single pixel of the real-world image. And it's actually different from the optical-based approach, which is using a direct view of the real world with overlaid graphics on top. Now, in the optical-based approach, the field of view is often an issue, and some of you may have noticed that. And the other disadvantage is that you can't really easily portray dark or opaque images, as you only have an additive solution in this type of displays. Now, in the following slides, I'm going to talk about the 4 main modules included in the SRWorks SDK. And these include the video see-through capabilities we mentioned earlier, where we can view the real world through the headset. Depth sensing, in that we can actually acquire depth information of objects in the real world, so getting the real distance between the HMD and the real world. 3D reconstruction and spatial mapping, it allows us to get information regarding the geometry of the real world and reconstruct the 3D environment scene, or even save and export it. And finally, we have AI vision and semantic segmentation that allows our system to understand the type of specific real-world objects around the user. So here's the generic architecture of SRWorks. It's very simple and flexible. It only has 3 layers: input, process, and output. And SRWorks implemented a dual camera adapter driver for you to acquire the video stream from dual camera as an input, and the output, of course, is a rendering driver to show the results to display. Now, in between the input and the output, we have the process, which is a function block pool with different modules connected to compose a pipeline. Each module can use the input from another module and create a new output. For example, the depth module can get the see-through image feed and estimate the depth information, and then that feed can go to the 3D reconstruction module that will in turn receive the depth map and process it to reconstruct a 3D model. The main purpose of the video see-through functionality is to provide users with human-like stereo vision perception. As we mentioned, the SDK, SRWorks SDK, implemented the dual camera driver for you to acquire the video stream from the dual cameras of the headset and then send it to the see-through function block. Now, because we want a wide field of view, for example, normally the headset has a fisheye camera, which comes with a bit of distortion, and SRWorks will handle this and convert it to a pinhole model to remove that distortion. So let's see what other tasks are available with the SDK inside the see-through. Now, the main advantage is that we can manipulate every single pixel. The SRWorks SDK allows you to apply different visual effects through materials on the video feed. So, for example, in the sample demo that is included with the SDK and is actually shown in the video here, what you see is the user spawning virtual spheres that represent different material effects. And as the user is moving the spheres closer to their face, you can see the video feed is getting modified. So this is great because since you can modify every single pixel in the screen, you can apply different material effects. So one could use this feature to create, for example, a Terminator vision effect or apply another shader. The sample demo in Unreal Engine comes with an actor that has an array of different materials, so you can easily just start testing this. Now, another feature that comes with SRWorks SDK has to do with depth acquisition. Developers can acquire depth information of the real environment, getting the real distance between the HMD and the environment. And that's really important because the depth data can then be used to align properly the virtual and real-world objects and achieve proper occlusion. So we can actually do proper occlusion handling of objects according to the relative distance, so placing virtual objects in the foreground or background depending on whether the real objects are in front of us or behind. Now, using the information from the depth data, we can get important information regarding the real-world scene and depth map the area around us. Now, SRWorks allows you to generate a dynamic depth mesh, which is nothing more than a 3D mesh collider produced from depth information that is updated every frame. It's called dynamic, and it's different from another mode we'll show soon, because it's updated continuously. So if you move your view from one to the other, the previously generated mesh collider is gone. Now, the depth map can be configured dynamically, so you can select your interested distance range. For example, if you only need to track your hand, you could set the detection range around your arm length. That's what the left image here shows. It's a rendering example of the depth map. You can see it rendered on a plane using a color gradient to represent distance. And below it, you can see a menu where you can change the slider values to fit your needs. Now, on the right image, you can see the dynamic mesh collider generated. Again, these are all included in the sample demo. Now, because we already have the depth information of the real environment, we can apply it into the Z buffer of the 3D engine. Therefore, the 3D engine will know how to mix real and virtual objects according to the relative distance to handle occlusion properly. If you look at the image on the screen, the white spheres are actually virtual objects, while everything else belongs to the real world. Now, with proper occlusion, you can easily understand the position of the white digital ball that is in between your real hands. And this is actually a lightweight approach for occlusion effect without creating any mesh collider. However, if you want to be able to interact with the spheres and actually, for example, use physics, then you need to enable the dynamic mesh feature so that the 3D engine can simulate physics collision. Now, let's see an example of occlusion handling based on the depth data. In this video, you see that the system will detect that the bug is in front of the virtual object. In this case, it's a virtual fox character. And in terms of relative distance, you'll see how when the bug goes in front of the virtual object, we stop showing the virtual object. And as you can imagine, that's something that is essential when it has to do with AR applications and interactions, because it gives you a better sense of depth, and it actually makes you feel that the virtual object, the virtual character in this case, lives in the real world with you. Now, the next feature is 3D reconstruction. This allows us to achieve spatial mapping, and it's different from the dynamic mesh in that, as you can see from the video, it continuously fuses the generated mesh frame, and it does this frame by frame. So we can reconstruct the entire physical 3D environment in front of us, and we can actually interact with the real world. And what you see here in the video, fusing the meshes frame by frame, once we're done with the processing, you can load the scanned results directly to view the mesh in front of you, or you can actually get the scanned result and export them as an OBJ file together with the collider for later use. So the SDK allows you to access information about the collider's properties, including things like orientation, shape, and area size. An API is provided for you to filter out those types of surface that you desire. And this is really useful because you can, for example, get the largest horizontal collider plane and set it as a navigation mesh that can be used for AI avatars, for example, or for other virtual objects. Similarly, you can also get other things like the bounding rectangle of the colliders or the approximate area size. Now, the last feature has to do with intelligence and spatial awareness. The SDK can not only give you information about the 3D geometry, but it can also tell you what kind of objects are around you. That's really useful because we can use that information and as we interact with the real and the virtual contents. Since we know the properties of the physical objects, we can make the virtual world do something according to it. So if you look at the video on the right, we have a demo video where we scan the environment, we scan those 3 chairs. The SRWorks SDK will detect that these are actually chairs and where they are in the physical world. And then a virtual character can be spawned and walk in the real world, and actually, as you can see, they can take a seat on a physical chair that was detected earlier. So you can imagine how this actually blends, again, the physical surroundings and the virtual characters. Now, with the AI Vision module, you can do 2 types of semantic segmentation. You can do 2D segmentation and 3D segmentation. We actually have a list of predefined objects to do that. Now, 2D segmentation is called 2D because it's based on the image feed. So it's about the pixels. Now, we can classify each single pixel in an image to belong to one class of objects, as you can see on the image on the left. And this shows a segmentation result. So you'll see how the chairs, the doors, the floor, and the wall are being detected and are rendered with different colors. And although initially we provided support for up to 9 different objects, as you can see from the table there, that list is getting longer and longer. And with every new update, we're adding more features, more objects that the SRWorks SDK can detect. Now, on the other hand, 3D segmentation allows us to get segmented mesh results in 3D format. This process runs in the background when performing spatial mapping, and when the scan is finished, the recognized objects can be segmented out. After that, we can, for example, point out to a real chair to show the segmented mesh result in 3D format, and you'll notice on the right-hand side a small chair icon on top of the physical chair. And on the left-hand side, you'll also notice that we can now get information about the detected objects and render the mesh accordingly to highlight the difference between the detected object types. Okay, so if you want to learn more things about all the SDKs shown today, the eye tracking SDK, the hand tracking SDK, and the SRWorks SDK, you'll find again everything you need online at developer.vive.com. Feel free to visit the website after this presentation and explore it. And the last thing I want to say is that since we were really disappointed when we realized that GTC had to be cancelled this year, and we weren't able to connect with developers there, we also have a full slate of live webinars coming in the next few weeks. We have already started actually, and we have 3 more left. But feel free to register and actually watch them, really interesting. And you can do it from your place now. So thank you very much, and I'm really glad to and happy to answer any questions.